Look up at the night sky, and you're looking into a space that spans 93 billion light-years across. It is a distance that far exceeds the reach of our own Milky Way, encompassing hundreds of billions of other galaxies. We know these exact measurements, yet we are physically trapped on a tiny rock. We obviously cannot unspool a physical tape measure across the vacuum of space to check our math. To measure objects we can never reach, astronomers use a method called the cosmic distance ladder. To determine the distance of a star, you must first establish a confirmed, mathematically rock-solid baseline measurement closer to home, and use that localized number to calculate the next step out. This mathematical chain reaction began over 2,000 years ago, with ancient Greeks studying simple shadows cast on the ground. Every calculation we hold of the deep cosmos depends entirely on the solution to that first localized geometric puzzle right here on Earth. The very first rung of the ladder was built by Eratosthenes in the 3rd century BCE. He noted a specific phenomenon. At noon on the summer solstice in the Egyptian city of Syene, sunlight hit the bottom of a deep well perfectly straight down. But further north in Alexandria, a vertical stick cast a small shadow. This diagram illustrates exactly how he solved it. By measuring that shadow, Eratosthenes found the sunlight arrived at an angle of roughly 7 degrees. Because he knew the physical distance between the two cities, he could extend those lines to the center of a spherical Earth and calculate its radius to be about 6,800 kilometers. Once we had the size of the Earth, we could look up. A few decades later, another Greek astronomer named Aristarchus realized he could use this new Earth baseline to measure the moon. He started by observing a lunar eclipse. Look at this model showing the Earth passing between the sun and the moon. Aristarchus carefully tracked the curvature and duration of the Earth's shadow as it cleaved across the lunar surface during an eclipse. Because he already had the physical diameter of the Earth from Eratosthenes, he could geometrically deduce that the distance to the moon was roughly 60 Earth radii. Securing the distance to the moon gave humanity its first extraterrestrial baseline. With that specific number locked in, mathematicians had the leverage to reach deeper into the solar system. The third rung of the ladder required precise timing. Aristarchus carefully observed the sky to find the exact moment when the moon was perfectly half illuminated, and then measured the angle between that half moon and the sun. This animation shows the right triangle created by the Earth, the half moon, and the sun. The math proved that the sun was situated at a vast distance compared to the moon, meaning it had to be significantly larger than the Earth to appear the same size in our sky. That geometric calculation led Aristarchus to argue, 17 centuries before Nicholas Copernicus, that the Earth must orbit the sun, not the other way around. Mapping the Earth, moon, and sun was relatively straightforward, but the planets wandered erratically across the night sky. It took centuries before astronomers like Copernicus and Johannes Kepler took on the mathematical challenge of charting those planetary paths. Kepler faced a specific mathematical puzzle. To map the solar system, he needed to track the true orbit of the Earth, using Mars as a reference point. But you cannot easily triangulate your position when both your observation deck and your target are moving at different speeds. Kepler's solution was to rely on time. Astronomers already knew that Mars took exactly 687 days to complete one trip around the Sun, its synodic period. Kepler realized he could use that specific cycle to turn Mars into a fixed anchor in space. This overhead diagram demonstrates his method. By recording the exact angle between the Sun and Mars, precisely 687 days apart, Kepler knew Mars would be in the exact same spot, even though the Earth had moved. Drawing triangulation lines between the Sun, Earth, and that point on Mars allowed him to map the true elliptical orbit of the Earth. By mapping the Earth's path, Kepler confirmed the astronomical unit, the precise average distance from the Earth to the Sun. Locking down the geometry of the inner solar system provided the long-range ruler humanity needed to finally measure the stars. With the astronomical unit established, scientists could use a technique called parallax. By looking at a nearby star in January, and then looking at it again in July when the Earth was on the opposite side of the Sun, the shift in the star's apparent position revealed its distance. Measuring nearby stars provided the baseline to measure distant pulsing Cepheid stars, which in turn allowed us to calculate the distance to other galaxies. When we view high-resolution images of infrared light from the earliest galaxies today, captured by modern hardware like the Hubble and James Webb telescopes, we are still relying directly on that same mathematical chain. Even the greatest modern astrophysicists were stepping onto the higher rungs of a ladder established by Kepler and the ancient Greeks. Humanity successfully mapped a 93 billion light-year universe. We didn't do it just by building better technology, but by applying relentless logic to a stick and a shadow in our